demonstration insight from source. Again, the C# transaction scope demo in our source nails this. The code just uses new transaction scope. No explicit isolation level mentioned. It opens a connection inside this scope, immediately checks the session's isolation level, and sure enough, the output shows serializable. Then it reads a range of data, say products 100 to 200. Because it's serializable, it slaps a range lock on that key range. The demo then tells you, go to SSMS, try to insert a new product, maybe ID 150, right into that range. And what happens? Your insert in SSMS just hangs, blocked, until the C# app finishes its transaction scope. It perfectly confirms that the restrictive serializable behavior, including those phantom preventing range locks, is active purely because of the framework's default. The developer might have had no idea. Action proposed for the cloud database professional. This is a huge call to action. Audit and educate. You need to audit the data access frameworks and ORMs your teams are using. Understand their default transaction behaviors. Where you can, explicitly configure more sensible defaults, like read committed, or even better, read committed snapshot if you've enabled RCSI. Make sure developers know about these critical framework defaults, so let them get caught out by hidden serializable traps. 3.3 driver level settings and implicit transactions. Explanation. Okay, this one's a bit more historical, but still good to know about. Even the database driver itself, ODBC, JDBC, 8.0.NET, can have settings that affect transactions. The classic example is set implicit transactions on. If this setting is enabled for a connection, then any data statement, select, insert, update, delete, automatically starts a transaction. And that transaction stays open holding locks until you explicitly commit or roll back if you forget. Locks held potentially forever. Historical context. Now, why does this even exist? Well, it was actually the default for really old SQL Server ODBC drivers. We're talking MDAC 2.5 and earlier. Think drivers used with SQL Server 6.5, 7.0, maybe early SQL 2000. The reason was backward compatibility with an even older library called DB Library, which basically worked in an auto commit off mode. It's a real relic from the past. Modern context. Here's the crucial part for you today. All modern drivers have implicit transactions off by default. SQL Server native client, the newer ODBC driver for SQL Server, versions 11, 13, 17, 18 plus, they all default to OAuth. So for any reasonably new development, you generally don't need to worry about this specific default setting biting you. The risk, however, if you happen to be working with some ancient legacy application, maybe one that hasn't been touched in 15 years, and it might still be using those old ODBC drivers, this could be the source of mysterious long-term blocking. A simple select could start a transaction that never gets committed, holding locks for ages. It would be incredibly hard to trace without knowing about this obscure historical driver behavior, the kind of thing that makes you tear your hair out. Action proposed for the cloud database professional. Just be aware this exists, especially if you inherit ancient systems or run into truly baffling blocking problems. For modern work, it's not really a concern, but it's a good reminder, isn't it? Always be mindful of the connection and transaction lifecycle. Make sure transactions are opened explicitly and always close promptly with a commit or rollback. Don't leave them hanging.
Right. So reading about dirty reads, non-repeatable reads, phantoms, it's one thing. But actually seeing the impact, understand what it means in a running system, that's something else entirely. Now, we're not going to run code live here on the deep dive, obviously, but our source material has these excellent T-SQL demos. They walk you through exactly what happens in these real world scenarios. It's fascinating, actually. You can even try them yourself later to really make it stick. Let's walk through what these demos show us. It's almost like doing a forensic analysis of common database problem.
Indeed, and they're designed perfectly for that. Usually run in two separate SSMS query windows, right? To simulate concurrent users, they really expose the subtle differences between the levels. 4.1, scenario 1, the non-repeatable read committed default. Objective. Okay, this one's about showing clearly how the default level, read committed, can give you different data within the same transaction if someone else commits a change. It's not just theory, it's a real issue. Observe behavior insight. So imagine, connection 1 starts a transaction, reads a hyperspanner widget, sees quantity 50, okay? Then you make connection 1 pause, maybe wait for delay 0.90. While it's paused, you jump to connection 2. Connection 2 quickly updates that same hyperspanner quantity to 45 and commits. Done. Now connection 1 wakes up from its pause, it runs its second select statement still inside its original transaction, and boom, it now sees quantity 45. What happened? The data wasn't repeatable within connection 1's transaction because read committed only holds that shared lock while the individual select is running. Once the first read finished, connection 2 was free to jump in, get an exclusive lock, change it, commit it. Connection 1's next read saw the new reality. It's like checking a sign, turning away, looking back, and the sign's changed. Why it matters. This is critical. Business logic might make decisions based on inconsistent data within one logical operation. Think about an accounting system calculating some complex total. It reads from table A, then table B. If data in table A changes after the first read but before the second, your final total could be subtly wrong. Leads to reconciliation nightmares down the line. 4.2 Scenario 2. The dirty read uncommitted NOLOCK. Objective. This one is designed to be dramatic, to show the absolute danger of reading uncommitted data, the chaos an O+K can cause. Observed behavior insight. Okay, connection 2 starts a transaction, updates flux capacitor quantity to 9 on E9, but crucially does not commit, holds that exclusive lock. Then connection 2 pauses for, say, 15 seconds. While it's paused, holding that uncommitted change, you go to connection 1, and you run a select using the NOLOCK hint. Connection 1 reads instantly, bypasses the lock, and what does it see? Quantity 999. Now connection 2 finishes its pause and does a rollback, undoes the change. The 999 never officially existed. If you now run a normal select, in connection 1, you'll see the quantity is back to the original, maybe 10. That 999 was a ghost. Catastrophic implication. The key takeaway. Connection 1 saw and potentially acted upon data, quantity 999, that never officially existed in a committed state. It was a phantom value, a dirty value. In a real app, this leads to wrong inventory counts, bad financial calculations, logic errors. Acting on transient data that vanishes leaves your database inconsistent, your business logic flawed. This really shows why NOLOCK is so risky for anything where accuracy matters. It's like building on quicksand. 4.3 Scenario 3. The phantom read, repeatable read. Objective. This one shows how repeatable read does its job, stops existing rows from changing, but is still vulnerable to new rows appearing that match your query filter. Highlights that subtle difference between row consistency and set consistency. Observe behavior insight. All right, connection 1. You explicitly set transaction isolation level repeatable read. Start a transaction. You select all widgets with spanner in name. Maybe you find just one. Hyperspanner. Okay. Connection 1 pauses for 10 seconds. During the pause, jump to connection 2. Connection 2 inserts a totally new row. Nanospanner also has spanner in the name, right? Commits it. Connection 1's pause ends. It runs its second select do. Same query, same transaction. And surprise! It now finds 2 rows. Hyperspanner and the new nanospanner. Why it matters. See, repeatable row worked as advertised. The hyperspanner row didn't change. It was stable. But its view of the set of data changed. A new phantom row appeared that matched its where clause. This can mess things up if your app, say, does a count first, then loops through rows expecting the count to match. Or if a business process needs a truly static view of the entire data set, including preventing new additions for its whole duration. To stop this phantom, you need serializable, which, as we know, has its own heavy costs. It's the difference between making sure this book stays on the shelf versus making sure no new books appear on the shelf at all. 4.4 Scenario 4. Reader-writer blocking, read committed versus RCSI solution. Objective? Okay, this two-parter is super important for every cloud database professional. It shows the classic blocking problem with default read committed and then the elegant solution using RCSI. Part A, the blocking problem. Observed behavior insight. Connection 2 starts a transaction, does an UP date on standard gear, maybe changes its quantity, holds that exclusive lock for, say, 15 seconds. Doesn't commit yet. Immediately after connection 2 starts, you go to connection 1. Run a simple select from debo.widgets. What happens? Connection 1 just, it shings, waits, doesn't return data for the full 15 seconds until connection 2 finally commits. That's textbook reader-writer blocking, super common, super frustrating. The reason users call saying, the system's frozen. Part B, the RCSI solution. How it works, this is the game changer. First step, enable RCSI at the database level. This starts with the command, alter database, your database name set, read committed, snapshot on. This fundamentally changes how read committed behaves for all future connections to that database. Reads stop using shared locks. Instead, they read from the version store in temp to DB. They don't need to wait for writers. Observe behavior insight. Now, run the same demo again after enabling RCSI. Connection 2 starts its long update, holds the lock. But this time, when connection 1 runs its select from debo.widgets, it executes instantly. No waiting. It reads a consistent version of the data, the quantity before connection 2 started its update, from the version store in temp DB. Key benefit. This is huge for concurrency. Writers don't block readers. Readers don't block writers. It massively improves throughput, responsiveness, allows your app to handle way more simultaneous work without getting bogged down in lock contention. Often, it's one of the single most impactful config changes you can make for performance without touching application code. Action proposed for the cloud database professional. This demo should really motivate you to look hard at enabling read committed snapshot, RCSI, especially for your OLTP workloads. It's frequently one of the best things you can do for concurrency and blocking reduction. Yes, there's more load on TempDB storing row versions, but that slight increase is almost always a fantastic trade-off for the massive gains in performance, user experience, and fewer blocking headaches to troubleshoot.
Okay, so we've gone really deep into SQL Server's world, how it handles isolation, concurrency, locking. But how does this approach compare to other big players? Oracle, PostgreSQL, MySQL. What's really fascinating is, well, it turns out there's some pretty fundamental differences in how they tackle this whole concurrency control thing.
Don't miss out. Smash that like button, subscribe, and explore our other videos in the playlists.